Building a machine that can see its environment, map a room, and navigate entirely on its own usually requires thousands of dollars in specialized hardware. But by combining standard, low-cost microcontrollers with the processing power of an older Android phone you likely already have in a drawer, you can engineer a highly capable robotics platform. This diagram breaks down the complete bill of materials. The ESP32 controller is $8. Drive components, including motors and chassis, are $27. Sensors like ultrasonic and orientation modules add $13. Power and battery bring the entire physical bill to exactly $86. Assembling and programming these parts will take between 8 and 15 hours. Before starting, you will need to install two pieces of software on your computer: the Arduino IDE, an application used to write and upload code for microcontrollers, and Android Studio, the official development environment for building Android applications. By following this specific hardware blueprint, hobbyist electronics can be elevated into Rover OS, a functional robotics operating system accessible to anyone willing to build it. Step 1 is the physical assembly. We start by mounting the DC motors, the ultrasonic sensors, and the L298N motor driver directly to the four-wheel drive chassis. The L298N motor driver acts as the heavy lifter for the system. It takes low-power, 3.3-volt logic signals from the microcontroller and uses them to switch high-power current to the physical wheels. Cautionary: this diagram illustrates the primary power circuit, highlighting a critical danger zone. The system is powered by a 3-cell LiPo battery, which provides 11.1 volts. That is perfect for the heavy-duty motors, but far too high for our delicate ESP32 microcontroller. To fix this, we route the battery power through an LM2596 step-down regulator. Using a multimeter to measure the output, you must physically dial the regulator down until it outputs exactly 5.0 volts. Only then is it safe to connect the line to the ESP32. Skipping this calibration and routing 11.1 volts directly to the ESP32 will instantly destroy the main logic board. Isolating the high current physical drive power from the low voltage processing logic ensures power spikes from the motors cannot damage the delicate sensors. With the hardware safely wired, we move to the firmware stage to configure the ESP32 microcontroller using the Arduino IDE. To parse data, track location, and control servos, you need to install 3 specific dependencies via the library manager: Arduino JSON version 6, Tiny GPS++, and ESP32 servo. Before uploading, verify your flash parameters match exactly. Set board to ESP32 dev module, CPU frequency to 240 MHz, and upload baud rate to 921600. Once the upload completes, check the physical board. A blinking onboard LED confirms the ESP32 is successfully broadcasting its BLE, or Bluetooth Low Energy, signal. This code turns an inert piece of silicon into a real-time wireless receiver, ready to translate commands from the phone into physical movement. Next, we configure the highest-level computing tier, turning the Android smartphone into the primary brain. This diagram shows how visual object detection works. The raw camera feed passes through a MobileNet V2 SSD COCO model. This lightweight, pre-trained machine learning model detects and classifies 80 common objects, like a person or a chair, directly on mobile devices without internet access. To integrate this model into Android Studio, you must place the detect.tf light model and its corresponding labelmap.txt file exactly into the app, SARC, main assets folder. You will also need to add specific user interface assets to render the data on the phone screen, including the ShareTech Mono font and colored XML drawable files for the red, yellow, and green status dots. Warning tone: do not place these machine learning assets in the root directory. Doing so is the most common failure point and will cause the application to crash immediately upon booting. Mapping these files to their exact required paths bridges the raw mathematical operations of the neural network into a stable, usable graphical interface. To initialize the Rover, mount the phone to the chassis, power on the battery, and connect the app to the ESP32 over Bluetooth. In the first test, obstacle avoidance mode, the Rover reads the front and side ultrasonic sensors every 50 milliseconds. If an object is detected within 15 centimeters, it will automatically steer toward the side with more physical clearance. This diagram illustrates SLAM mode, which stands for simultaneous localization and mapping. As the rover drives, it translates the raw distance pings from its ultrasonic sensors into a live digital occupancy grid, marking detected obstacles as solid blocks on your phone screen. However, you will encounter real-world hardware limits. The GPS module can take 2 to 5 minutes to secure a cold start lock outdoors. Inside, the SLAM map will slowly drift out of alignment because it relies on dead reckoning, estimating position based only on motor speed and the IMU, or inertial measurement unit, which tracks orientation. Navigating real-world physics requires accepting these noisy sensor readings and planning future engineering solutions to account for them. With the assembly complete, the rover successfully integrates computer vision, spatial mapping, and physical movement to navigate a room on its own. Right now, the system operates at about 80%. That remaining 20% is not a failure of the design. It is the natural threshold where software limitations require hardware upgrades. This diagram shows the solution to the SLAM drift. By installing precise quadrature wheel encoders to measure exact physical rotation and applying a Madbic filter, a mathematical algorithm that smooths orientation data from the IMU, the drifting path resolves into a highly accurate map. Building Rover OS to this milestone provides a stable foundation. From here, adding new sensors, writing better control loops, and refining the code becomes an endlessly scalable journey in autonomous engineering.